So what I'm going to talk about is, in some sense, like it's very much related to what we heard in the last talk, or there's some kind of additional feature that I want to talk about, and that's named this string coproduct or string cobracket. So the setup that we're in is M is a closed manifold, and Lm will be the free loop space. So then, as was explained before, then on the homology of the loop space, there's certain operations, and amongst them there is what is called the Sullivan product, which geometrically is defined as follows. So we take a class in, or two classes in loop space homology. So maybe here the red and the green class. Then we can look at where they, so now we have a, sort of a family of loops, and we can evaluate each of those loops at, let's say, the time 0. So this gives you those spines. Now you can ask, where do those spines intersect? So it's only at that point. So at each point where they intersect, we get 2 loops, and we can compose those loops. And this gives us, again, some class in this loop space homology. Then there's an additional operation that I also want to talk about. That's what is called the Goreski-Hingsten coproduct. So it's sort of similarly defined to the Sullivan product, except we want to do the same now just with a single family of loops, and we want to count self-intersections. So geometrically, how it's defined is or maybe here a bit more precisely. So we think of having some kind of family of loops here parameterized by some parameter space P. Again, we think of like some kind of a picture like that, and now we want to focus on the set of loops where the loop intersects itself at time 0. In particular, we can define the space of parameters and times where the loop at time 0 is the same as the loop at time t. And we exclude that the time can be 0, because at 0 we would also always get sort of trivially those intersections. Now, at each of those points, we can now define 2 loops, because we already have, or at each of those points, we have a loop that intersects itself, so we can split it into 2 loops. Or in formula, we take a loop at time p. If you're restricted to the interval 0t, that's still a closed loop. And likewise for the rest of the interval. Now, the way I've written down this definition is as a slight problem, namely it's not really well defined. And the problem is that, or the problem comes from kind of small loops. So namely, if you take a family of loops and you sort of introduce these very small loops, then you get intersections on the left-hand side, but you don't have them on the right-hand side. So now, if you were to compute just given the recipe that I gave above, then you'd get different answers for those 2 things. Then on the left-hand side, you sort of split off this small contractible loop, and on the right-hand side, you didn't. So there's kind of a thing that we need to fix, and there's 2 ways to how this can be done. So the first is just realize that this is the only thing that can ever happen. So namely, just whenever we get those small contractible loops, we throw them away. So here, M sits inside of the loop space of M as small contractible loops, or actually constant loops. Or there's also a different solution how one can fix this problem, and that's if you have to choose a non-vanishing vector field on M, then you can also sort of make this ambiguity go away. So particularly in that case, we need that the Euler characteristic is 0. And yeah, so going on, everything that I will say sort of works for both those cases. Right, then, so again, as we saw in the last talk, on loop space, we have natural circle action just by rotating. So this gives us a degree 1 operation on loop space. And basically what was already mentioned is that, so what at least part of what I described is this, it's part of this PV structure. So if you go to fixed points or orbits, then you're supposed to get a Lie algebra. And here we can do the same thing with this sort of co-algebra structure. Or to be more precise, so we have there's a map from the equivariant loop space homology. So here I want to think of them as sort of families of unparameterized loops. And you can reparameterize them, but if you have sort of an S1 family of choices. And similarly, you can just forget the parameterized loop to an unparameterized one. So in particular, I have sort of maps in both directions from equivariant loop space homology to loop space homology. So I can just take my previously defined operations, just compose with those two maps to define maps now in this equivariant loop space. So here, the claim is that if you do that, then you're going to get an involutive algebra. And now it has some sort of consistent degree. So the bracket and the cobracket now both degrees 2 minus n.
Sorry, Florian, I'm not sure about other people, but for me the sound doesn't work very well. Could it be that you are, whatever, doing something with your microphone?
Well, for me, it doesn't work. There are some stops between voices.
Okay, could you say something?
Yeah, can you hear me better now?
Yes. Yeah, it's good.
Oh, maybe I'll just try to speak louder. Does that help?
Now it's good.
Okay. Right, so as I was saying, so we have either those two operations on just loop space homology, or we can consider them on equivariant loop space, on like the space of unparameterized loops. And on unparameterized loops, now we get not only a Lie bracket, as was explained before, but now we also get a cobracket. And they are compatible in a way of that they form an involutive Lie algebra. So now the goal is sort of to try to compute this structure or like give some kind of model of it. And here, as a model, I want to have a model in the sense of rational homotopy theory. So for that, let's recall the following thing that, so if you take the algebra of, let's say, differential forms, or any other sort of rational model of your manifold, then one can identify sort of this loop space homology with Hochschild homology, or sorry, a bit more precisely, so Chen defines a map from Hochschild chains. So for me, CH is going to be Hochschild chains into some version of differential forms on this infinite dimensional space of loops. And he shows that this is a chain map. And moreover, if M is simply connected, then this is a quasi-isomorphism. So in particular, we can compute loop space, I guess here loop space cohomology in terms of Hochschild homology of differential forms, or of any other model that we have for our space. So now the question that we want to answer is, or at least that we can ask is, so now on loop space homology, or then dually on loop space cohomology, we have those two operations in the product and the coproduct. So can we sort of describe them on this Hochschild homology side, and what, like, do we need additional information, or like what extra data is needed? So the first answer that we can give is, like, in certain cases, namely if M is simply connected, then you can choose a particularly nice model for the manifold or for differential forms. And in that model, you can sort of just, let's say, compute, or there's sort of a straightforward algebraic model that is least a good candidate. So for that, we need to first recall, so if M is a simply connected manifold, then there exists actually a very sort of good model for cochains, in the sense that they satisfy binary duality strictly. So it's a finite dimensional algebra that has an inner pairing that is non-degenerate.
So Florian, so it's not a model in the sense of Sullivan.
Which one?
The A. When you say it's a model, it's not a model in the sense of Sullivan.
I mean, it's supposed to be a CDTA together with, or like equivalent to, let's say, differential forms.
Right. Okay. Yep.
Right, so it's not like a Sullivan model, if that's what you're
Right. Yeah, that's, yeah. No, not in, it's not a model in the technical sense. That's what I was double, you know, yeah, right.
Like, so in particular, what Lambert-Stanley showed is that you get like this model in this non-technical sense, just an algebra which is quasi-isomorphic to differential forms, but it said it has this additional Euler property. So in particular, you can say it's a DG Frobenius algebra, except there's
sorry. Now we again get a little bit of problem with sound.
Yeah.
So what do you change?
Nothing really.
Okay, okay.
I think if I'm further away from the microphone.
Oh yeah. Okay, maybe then stay close.
Yeah, I'll try not to relax then. Right. So in particular, if M is simply connected, then we can choose a model that has some additional property. And it turns out if you are given a Frobenius algebra, then you can sort of take your favorite model, like the standard model for chain algebra, and this carries, you can sort of algebraically construct all types of string topology operations that you could wish for. But here we're only interested in basically those two operations, or actually mostly interested in the coproduct. So let me just say write down the formula for the coproduct. So here what you're doing is you take two Hochschild chains, and you, in some sense, just you concatenate together those Hochschild chains.
My apologies. I'm always complaining about this sound, but I don't know whether it works for other people.
I
have problems too. Yeah.
Yeah, but sometimes
I change my computer, so maybe that's just a second.
Sometimes it works very well.
Yeah.
For instance, now.
Yeah.
I mean, some people suggest maybe if you turn off the video, then who knows, at least we can try it. Okay, let's see what it gives.
Yeah. And tell me if it doesn't work again, then I can try to use a different computer. So, but now you can hear me.
Yes.
Okay. Right, so in particular for this, like the model that is given by this construction of Basper and Klump independently is that so the coproduct, you just in some sense just concatenate together those two Hochschild chains, and you have to sort of add in the diagonal class of this Frobenius algebra. So it turns out that this construction is a chain map. But now what we can show is that, so in the case where M is simply connected, then now you have sort of these two sides, these two constructions. Either you can take the geometric one and sort of pull it back along chain isomorphism, or you can take directly this geometric one. And it turns out that they are the same. So Chen's natural map, it intertwines those geometric and the algebraic structures. And as above, we saw that the Lieb algebra structure that's just induced by sort of the string product and coproduct. So in particular, we directly get sort of the same result for the cyclic homology. So namely the sort of the natural algebraic Lieb algebra structural cyclic homology is the same as, or is the correct one that comes from geometry. So let me maybe here just for concreteness, say a bit what this structure, or like at least on the cyclic homology, how this looks like. So I'm going to take here the following model for cyclic homology, and here I might be off by kind of cyclic homology or negative cyclic homology of a point. So what I take is literally cyclic words and I dualize it once again to have sort of more like a bracket will look again like a bracket, and cobracket looks again like a cobracket. So the model that I take for it is I take cyclic words in the algebra, or the dual of the algebra. So let's recall that because A was supposed to be a Frobenius algebra, or this parameter duality model, it comes with an inner product.
So, sorry, now it slightly degenerates again.
Yeah.
Yeah, maybe once the suggestion was maybe not directly face the microphone, but of course, well, it's difficult to say. Somehow you change something and it works, but then it degenerates.
Yeah, that's right.
Okay, let's continue.
Right, so in particular here, so I have to give or want to give a Lieb algebra structure or DT Lieb algebra structure on this space of cyclic words. And the way how we do it, so we think of a cyclic word as some kind of circle with labels in this A dual. So then to get a bracket, we sum over all pairs of labels and we connect them. So using a bridge, and whenever we connect them, we have to evaluate them using the inner product. And for the coproduct, we more or less just do the same thing, except now for a single circle. So we just look for all pairs of labels, we evaluate them against the inner product, and we build a bridge between them. So now in this one connected case where we can use the previous theorem, what we could also do is now we get this sort of involutive Lieb algebra structure on this, or DT involutive Lieb algebra structure on cyclic words. So we could try to do a homotopy transfer to just cyclic words in homology. And it turns out there's a sort of a theory of those involutive Lieb algebra structure up to homotopy developed by Sullivan, Foucault, and Lachev that allows you to do that. So particularly in the simplic case, you would get sort of a model on the cyclic words. Again, for these string topology operations. But it turns out that you can also do this in the non-simply connected case, but you cannot do it directly. So like you have to use some kind of different method or slightly different method. But it's still possible. So that's the second main theorem is basically that you can directly construct this Lieb algebra structure up to homotopy on this cyclic words of homology. Or here more precisely, so now we can take M maybe not necessarily one connected. So the statement is there exists such an involutive Lieb algebra structure up to homotopy on this cyclic words, such that if you take homology of everything, then this still computes sort of the correct cyclic homology. So namely here it's kind of the cyclic homology of the co-algebra of chains on the manifold. So then in particular, we can still identify this with loop space homology, or at least there's a map in one direction, so it's not necessarily an isomorphism. But we can say that that map is a map of Lieb algebras. So moreover here, the theorem this was conjectured by, like in this paper about involutive Lieb algebra by Sullivan, Foucault, and Lachev, and they already gave some kind of hint of how one is supposed to obtain this IBL infinity algebra, and that's also more or less how it appears in our proof. Namely, it comes about by what's sort of constructed using the partition function of a sort of Chern-Simons type field theory. Okay, so let me talk a bit about the ingredients of the proof. So, like, sort of the first main ingredient is just to get a sort of a proper or a more suitable description of the string coproduct. So the main problem, or just one feature of the description that I gave in the beginning is that, so there technically I should talk about some transversality issues, because I'm only supposed to take those intersections whenever they're transverse. So maybe first one should show that actually I can put every chain into a transfer position. And yeah, so here I'm gonna give a slightly different, or maybe more topological description. And at least the way it's supposed to work is as follows. So it's more or less composed of 3 steps, where only the middle one is the interesting one. So the first thing that we do is we take the class in loop space homology, and we just like suspend it once. So we just take the product with the fundamental class on the interval. So this is sort of like choosing or varying over all possible parameters. Now we want to look at when does our loop intersect itself at that other parameter. Or sort of a different way of saying this would be that, so we have from this loop space times the interval, there's a map into 2 copies of our manifold. And what we want to do is we want to intersect, so we want to intersect a class in here with the preimage of the diagonal along this evaluation. So this is sort of, we're gonna have to figure out how to actually do those intersections. But then, so the space that you land in is now, so this space of figure 8s, or it's the space of whatever lies over the diagonal under this map, and things that lie over the diagonal, so that's a loop and a time such that the loop at that time is again as the same as the loop at time 0. So it's the same as sort of a figure 8. And the way how this sort of relative intersection is supposed to work is you can also, like, it's sort of just those relative ones, they just in some sense just go along for the ride. Then you land into, so now those space of still figure 8s that are either one of those ears, it's just constant. And if you have such a thing, you can break those ears apart, such that you get 2 loops, and relative to either the first part or the second part is constant. So here the main problem, or the main thing is this: how do you do this intersections? And let me maybe try to formalize this a little bit, or simplify it, what kind of intersections we need to do here. So maybe let's assume that we have some kind of local system over m times m and some other local system over the diagonal, such that this sort of the system over the diagonal, it maps into kind of this big local system. And here the situation that we have in mind, so our big local system is supposed to be that map sort of Lm times 1 to m times m. And our sort of smaller local system that now lives only over the diagonal is here just 2 copies of the loop space. So now the type of thing that we want to do is we want to take some kind of relative homology and do intersections with the diagonal to get a sort of homology that now just lives on the diagonal, but is still relative with respect to those 2 local systems. And now there's at least 2 ways how to do this. So one way is sort of more like it's in paper of Hengst and Well. So the way how this works here is that, so first we have to choose a tuple neighborhood of m inside m times m. So let's call it u. So in particular, or because it's a tuple neighborhood, we can identify it with the tangent space, with the tangent bundle. So now what we can do is, so basically sort of this classical Thom construction, but being a little bit careful. So at first we just take it relative to everything outside of this tuple neighborhood. So then we want to use excision to identify this with just the Thom space, and the last step is we want to cap with the Thom class. And so one problem that, or like a slight thing that we need to be careful about is when we go. So when you go from here to here, what we actually want to do is, So we restrict our local system to this neighborhood of the diagonal, but we don't, so in particular, it might not be constant along the fiber direction. So but in the end, when we want to cap with the Tom class, so this, yeah, it cannot be non-constant. So in particular, we need to identify with the one that is constant along the fiber direction. And because they're local systems, the way how one would do this is you just choose sort of paths connecting, or roughly you need to know, or you need to choose a deformation retraction of this tubal neighborhood to M. Right. So there's also a different way of, or sort of a bit more canonical, or at least for our purposes, it's more canonical to do this. So the problem, or the features of the previous constructions are just, you need to choose a couple of things, namely to choose a tubal neighborhood, plus you need to choose a deformation retraction. And so instead of doing that, you can sort of choose your tubal neighborhood infinitesimally small. So namely, let's recall, so there is such a space FM2, is the Falden-McPherson compactification of the configuration space of 2 points. So the way you obtain this is you take 2 copies, or just M times M, you throw away the diagonal, and then you compactify in the appropriate sense. And the appropriate sense is as a set, it's just you throw away the diagonal and you glue in the unit tension bundle. In particular, when points get close, you remember at least which direction they were coming from. So now using this space, we can do in some sense the same construction as before, except we don't have to choose this sort of deformation retraction of that neighborhood. And then the way it works here is sort of similar. We first go from homology on M times M. We first sort of take it relative to FM2. So here, whenever we have a quotient, we should think of this as some kind of cone construction. So now excision allows us to identify, or sort of this quotient is kind of M times M minus M, and you glue in the unit tension bundle. But now we sort of throw away everything again. So it's just kind of the quotient of M, or of M and the unit tension bundle. So in particular, that's, if you take the cone of that, that's again just Tom space. And then the last step is again capping by the Tom class. And so in particular here, what kind of the things that we actually needed is that this space FM2, it fits into such a commuting diagram that turns out is a homotopy pushout. So in particular, I sort of identified there's the vertical co-fibers, there's just 2 versions of Tom space, where one version sort of naturally lies over M and the other one naturally lies over M times M. So, but in particular, now it's sort of clear that, so if you want to get a rational description of our coproduct, then sort of like the most difficult things is doing these relative intersections. And for that, it's enough if we understand sort of this diagram of spaces, or if you have a model of that diagram of spaces. And yeah, it turns out that these diagrams of spaces, or sort of all these configuration spaces of points, have been studied in work of Willwacher, Kampusch, and Idrissi, and they give explicit, so what kind of explicit models of all these configuration space of points together with all the maps between them that one could basically wish for. So in particular, that's just a very small part of what they get models for. And they in turn, they also give sort of 2 models for this situation. Maybe one model is again in terms of such a Frobenius algebra, or if you have a Lambert-Stanley model, and it's only valid in the simply connected case. And the more general model is in terms of a partition function. So in particular, like this is sort of like where these 2 occurrences come from in the theorem. But so now that maybe you understand a bit better how these things are constructed, so now let's try to, or at least discuss a bit what are they actually invariant under these things. So a priori should be more or less clear that whenever, like if we construct it correctly, then it should at least be invariant under diffeomorphisms. So two diffeomorphic manifolds, they're supposed to have the same string topology. But now the next question that we can ask is maybe something weaker is already good enough. So maybe if they're just homotopy equivalent, then they would still have the same string topology. So that question I cannot directly answer, but maybe a slightly related question is that, so let's not look at just a single homotopy equivalence, but let's look at the monoid of homotopy automorphisms. Those are just self maps of M, and you take the component containing the identity. So particularly if you take homotopy groups of these homotopy automorphisms, then they act on loop space homology. So now the question is whether our brackets and cobrackets are near equivalent one. So we can ask whether brackets and cobracket are actually invariant with respect to that operation. Or here invariant means whether these automorphisms, they act by derivations of the bracket and cobracket. So and here what turns out what one can do is that, so basically one can just or there is a rational model for these homotopy automorphisms, and if you compute it, then it turns out it's more or less just the direct summand of a cyclic homology. And under this identification, one can show that this action from before, this just becomes the adjoint action. So now our question about homotopy invariance, that just becomes the following. So you take an element in this Lie algebra, or actually in this sort of direct summand that corresponds to automorphisms, and the question is when does this correspond, or when does this give you the derivation of the bracket and cobracket? And yeah, for a bracket, it's always the case. So it's just the Jacobi identity. But for the cobracket, it turns out that it's at least not automatic. So the equation that you get by just playing around with sort of the axioms of Lie algebra is that it only preserves the cobracket if the cobracket of the element itself is either zero, or it acts on everything else by zero. And it turns out that this is just in general not zero. Like in cases where one can compute basically everything, it turns out that there are such elements that just are not zero in this state. And those examples where we can compute everything, that's the sort of higher dimensional analogs of spheres, of surfaces. So in particular, what you get from this is kind of an obstruction for let's say elements in automorphisms to actually come from diffeomorphisms. So what we've seen is that an element of the homotopy groups of automorphisms, if you sort of go through the cobracket and then let it act on everything else, then it's supposed to be, or for this to be zero means it preserves the cobracket, but not everyone might preserve the cobracket. So particularly you get some kind of sensitivity, or the string coproduct or cobracket, it is somehow a bit sensitive to more than just the homotopy type. And here sort of the thing is that these examples here, we can only really compute them for sort of higher homotopy groups, so those automorphisms. So we cannot really say anything for actual homotopy automorphisms. And there the problem is that sort of the algebraic model is not really the correct model. But this statement might still, so there might still be some kind of non-homotopy invariance. You can just not see it or not see it in this rational story. So now the question is, so where does this extra sensitivity come from? And here, I maybe describe, and so the following is trying to work with Paul Safronov. So let's recall from a previous talk that basically take or assigning this to the circle the loop space homology, and that's supposed to extend to 2D TFT. And here it was this sort of a left version or the smooth version where you're at least supposed to have one outgoing boundary. So in particular, what you get is for a pair of pairs, you get an operation, which is the string product, which was explained before. And for upside down pair of pairs, you also get a coproduct. But again, it has sort of the same dimension shift. So it's not the coproduct that we were interested in getting. There's an extra L missing. Yeah. Right, but because it's part of this TFT, or the coproduct, that's basically trivial in two different ways. So namely, you can define, or you can write the coproduct or you can factorize it in the following two ways. Or sort of in the formula, this is just some kind of Frobenius, or just kind of a Frobenius identity. So maybe you can compute the coproduct of X by just sort of multiplying. But just multiplying X with the coproduct of 1. So in particular, from this presentation, what one can get is, so if we now assume that this coproduct, also this trivial coproduct of 1 is 0, or you can trivialize it, then this identity becomes a secondary operation. In particular, for every, yeah, so for every trivialization, we get one of these secondary operations. Yeah, so the things that one cannot really read here, that's supposed to be, so either you have to trivialize it all the way, or it's also good enough if you can just explain that it sort of lies in the subspace. In the subspace of this loop space homology, and if you can explain that, then you get you might not get operations like that, but you get these type of relative operations that we saw in the beginning, sort of relative to constant loops. So in particular, let's call this notion something. So let's say a null homotopy of this coproduct of 1, let's call this an Euler structure. Here, sort of one remark is that at least this notion, this makes sense for any smooth DG category, because like that part of this TFT, it only needs the smooth part, and you don't need the Calabi-Yau structure. And one can think of it as some kind of non-commutative projective Falling form. So now back to our case. So as was explained before, like to get this, or to get sort of this loop space, so this string topology TFT, what we're supposed to put in is the algebra of chains on the base loop space. So in that case, we can actually say something more about this element. So namely, that element is obtained as follows. So let's recall if you take a module over an algebra, then, or each module over an algebra in particular gives you a characteristic element in Hochschild homology. So in particular, for that particular algebra, there is a module which is just sort of the constant, just the ground field. And if you take the class of that in Hochschild homology, then it turns out that this is the same as this delta 0 So there's a question. Well, why is this structure called? So let me.
I guess I can ask the question myself.
Yeah.
This null homotopy of delta 1 is called an Euler structure. I was just wondering why the name Euler structure.
Right. So the thing is that this element, like this characteristic element here, this is some kind of homotopy invariant version of the Euler characteristic. And it turns out that, and we're going to say this in a second, so this element, it always actually comes from just sort of constant loops. So it's an element in the homology of M. And it's actually an element in the zeroth homology of M. And the element that it is, it's Euler characteristic times 1. And now sort of, if you want to trivialize that, so you have to sort of explain why the Euler characteristic is 0 in a certain space. And there it turns out that there's a notion by Naef, and he called it an Euler structure. And in that sense, it's sort of like if you have a cellular complex, then you have to kind of pair, like if you have a cellular complex whose Euler characteristic is 0, then you can sort of implement this zeroness by sort of finding paths between corresponding simplices.
Right. So M is simply connected everywhere here?
No, here no longer.
So what do you mean by 1? When you talk about the homology of LM, what?
Right, so it's, I mean, so whenever you have this kind of smooth algebra,
yeah,
then it defines you like this, this TFT, and there is one, I mean, the operation actually.
You've written an equality there between Hochschild homology of A and homology of LM, and that is only true if. So the Hochschild homology of A always has a 1, but homology of LM only has a canonical.
I mean, the thing is supposed to be here. So you can identify Hochschild homology with Hochschild cohomology. And then that 1 is like either the 1 in one side or sort of the fundamental class in the other side. Oh,
so you mean, so you mean
I didn't fully
of a volume form.
So can you repeat that?
Orientation form. It has degree n?
Right, yeah, it has degree n.
Oh, okay.
No, it has degree 0.
Well, I don't understand.
So the one has degree n if you want.
Well, all I know is that the H0 of LM does not have a canonical element.
So the canonical element that it has is sort of the point times Euler characteristic.
Which point?
At any point. I mean, it's connected.
They're all different. I mean, you mean a contractible one?
That I don't understand.
I mean, so you're assuming M is connected.
Yeah.
Well, the free loops in M, there are many components. So when you say a point.
All right, it's in the component of the contractible loops. Sorry.
Yeah. Okay. Good.
Yeah. Right. And so in particular, like to go back to, so there's 2 types of doing relative intersections. You can see them as sort of finding these null homotopies of that Euler characteristic. So in particular, you can plug it into that sort of TFT machine to get the secondary operation. And it turns out if you take any of those null homotopies, then you're going to get the string coproduct that we talked about above. So now there's another thing. So there's kind of already a type of theory where people talk about trivializing this type of Euler characteristic. And that's you can, so you have this module or this algebra, and you can either say I want to trivialize it in Hochschild homology, or you can ask whether it can already be trivialized in K-theory. And it turns out in the question whether it can be trivialized in K-theory, that's sort of something well studied. And it turns out if you're given a simple homotopy type, then you can trivialize it, or more precisely, you can sort of lift it along what is called the assembly map. So you can explain why it's sort of not in this nonlinear theory, but it comes from kind of some just homology class. And it turns out in this lift, there is this extra information, which is the simple homotopy type. So in particular, if you take just this Dwyer-Weiss-Willems theory or this Dwyer-Weiss-Willems lift of that canonical Euler characteristic, then we can map K theory to Hochschild homology, and we again get this null homotopy. Then we can again try to construct we can construct a coproduct out of it, but we don't exactly know yet whether they are the same or not. So in particular, the conjecture is that they're all the same. So this kind of geometric way of doing relative intersections that we saw above, that's sort of equivalent to giving the structure of a simple homotopy type. Or maybe it's weaker, but in particular, it's compatible with the simple homotopy type. I don't wish it's so like that we cannot prove at the moment. But let me maybe just briefly say what would be a consequence of this conjecture. So in consequence is namely then we can understand exactly sort of in what way non-homotopy invariant the coproduct is. Namely, it transforms with respect to a term that you derive from the Whitehead torsion. So namely, if you have two manifolds that are homotopy equivalent but not necessarily, let's say, homeomorphic, then you get that the coproduct is not preserved by this homotopy equivalence, but you get an extra term. An extra term is sort of given by the action of the Whitehead torsion, or more precisely, you have to sort of take the Whitehead torsion, then map it to root space homology, and take the diagonal of it. So in particular, then it would be invariant not under all homotopy equivalents, but at least under all simple homotopy equivalents. And with that, I thank you for your attention.